Hello everyone, myself Ashit Desai, Assistant Professor, Mechanical Department. Today we are going to discuss here the unit number first, that is basics. So in last lecture we already discussed the properties of fluid. So first we have discussed the density, then specific weight, specific gravity, then specific volume. So in that lecture we will discuss the viscosity. So in that kinematic viscosity and dynamic viscosity. So first of all we look at the learning objective for this session. So first learning objective is to know the importance of fluid mechanics. Second learning objective is to know various properties of fluid mechanics. Now we'll discuss next, that is the learning outcome. So after this session some learning outcome is there. So first learning outcome is the student will able to know the basic content of fluid mechanics. Second learning outcome is the student will able to explain about the properties of fluid mechanics. So first of all we look at the property of viscosity. So the viscosity is nothing but the property of fluid which can offer a resistance to movement of one layer of fluid to all other layer of fluid. So here you are considered two layers of fluid with a separating distance dy, and it can move one over the other with a different velocity, so it can causes a shear stress. So that effect we can observe in that figure. So here we can say that shear stress is at bottom is maximum and velocity is almost zero. But if you increase the graph, what will happen? The shear stress is minimum and increasing the velocity. So this is the regarding the viscosity. So now we discuss next phenomena, that is viscosity. So if the top plate is at moving condition and stationary plate is at bottom, in between that we can place a fluid, or can say here the honey is there. So if you place honey, so it require more force. So more force means what? That more viscous. So honey is more viscous because it required more force. And if you consider for water, what will happen? It required less force, so that's why it called as a less viscous for water. Okay, so actually viscosity is nothing but it can determine the amount of resistance of the fluid to the shear stress. So this is regarding the viscosity. So we can take example of that: water, olive oil and honey. So for honey it requires more force, that's why it is called as a high viscosity. It is because of the intermolecular structure. So intermolecular structure is having strong, so that's why it required more force, so that's why it required called as a more viscous. If you consider for water, what will happen? It bonding is loose as compared to the honey, that's why it is called as low viscous. But in case of olive oil it should be medium because the strength of the intermolecular bond is medium, so that is called as medium viscosity. So this is the viscosity phenomena and this is the example. Now why you study this viscosity? So because of these reasons. So while applying the high load condition for the machines, we can use high viscous fluid, or can say high viscous lubricants. And if you required in a engine oil, so it can optimum range of viscosity is required. And for pumping session, so if you require the high viscous fluid is there, so that time it require high power for lifting the that viscous fluid. And if you consider for low viscous, what will happen? It required low power as compared to the high viscous fluid. And for blending fluid it requires less viscous, it can be easy to mix, and it can improve the characteristics of the fuel. So this is the importance of viscosity, so we can determine here, and then we can blending these two fuels, otherwise it should be not affecting aesthetics. Then if you consider in a coating and printing, so this is also important viscosity. Okay, so in the next slide we will discuss here the relation between shear stress and velocity gradient. So in the difference is the, you know, that relations, we can say that shear stress is nothing but tau and velocity gradient is nothing but du by dy, or you can say du by dy is nothing but shear strain. So whenever the shear stress is more, what will happen? The viscosity, the shear stress is always dependent on the two phenomena, that is with velocity and distance. So if your distance will increase between the two layers, what will happen? Two layers will be increases. Means what? That shear will be minimum. So another example we take here. If you're placing two plates, parallel plates, and if you will, that separated distance is dy. So if you decrease this dy, or you can say zero difference is there, so more shear stress is there. So that's why tau and dy is inversely proportional. And if you consider du, if your shear stress increases, that change in velocity also possible. So that's why it is directly proportional. So here the relations between there is tau proportional to du by dy, and for constant tau proportionality, that is mu, we can take it like this: tau equal to mu du by dy. Now we can take mu is on both sides. The mu is called as a constant of proportionality, right? Or you can say coefficient of dynamic viscosity. So for the purpose, mu is equal to tau upon du by dy. So by solving this, mu is one, we can take one side, and tau divided by du by dy. So that mu is called as coefficient of dynamic viscosity. Is it clear? So here the viscosity is defined as the shear stress required to produce a shear strain. So that is called as viscosity, right? So this is the phenomena for viscosity. Now we discuss here the unit of viscosity. So viscosity is nothing but mu du by dy. Sorry, that is tau du by dy. Mu is equal to tau du by dy. So mu is nothing but shear stress is equal to shear stress. So you can write tau instead of that, shear stress. Du by dy instead of that, change of velocity to the change of distance. Is it clear? For shear stress, we can take force upon area. Shear stress is nothing but force upon area, because tau is equal to F by A. And now change of velocity. So you can take length upon time into change of distance. We can take 1 upon length. So here cancels out length. So remains only force into time. Time is go upper side. So force into time divided by area. So we can write length square. So that equation becomes force into time length square. So force in terms of Newton, time is in terms of second, and length in terms of meter square. So unit is Newton second per meter square for viscosity. So we can say viscosity or dynamic viscosity. Okay. Now we move for the further units of viscosity. So in SI unit, the unit of viscosity is Newton second per meter square. So as you know that Newton per meter square means Pascal second. This is about SI unit. And in MKS system, so the unit is kgf into second per meter square. So this is regarding the MKS, and regarding the CGS system, that is centimeter gram seconds, the unit is dyne second per centimeter square, or you can say poise. So poise is the name of scientist. So 1 poise is nothing but 1 by 10 Newton second per meter square. So this is the regarding the viscosity. So whenever the conversion of poise to Newton second per meter square is there, we can divide by directly 10. So this is regarding the unit of viscosity. Now we move for next phenomena, that is kinematic viscosity. So as you know that kinematic viscosity is nothing but the ratio of dynamic viscosity and density of fluid. So the question is like that: what is the relation between the kinematic viscosity and dynamic viscosity? So relation is like this: the nu is nothing but kinematic viscosity is equal to viscosity upon density. So that viscosity is nothing but mu, we can write is, and density is in terms of rho. So after solving of this unit, we will get the unit is meter square per second. So unit of kinematic viscosity is meter square per second. So the difference between the dynamic and kinematic is the dynamic viscosity is always measured in terms of Newton second per meter square, and kinematic viscosity is measured in terms of meter square per second. So as per our requirement, we can measure accordingly. So now next we will discuss here that unit of kinematic viscosity. So how it comes meter square per second. So first of all, we write this nu is equal to viscosity of density, that is the relation between the dynamic viscosity and kinematic viscosity, right? So nu you can take as it is, then unit of mu divided by unit of rho. So here mu is nothing but dynamic viscosity, right? So what is the unit of that? Newton second per meter square. Newton means force, so I write force, then second means time, and divided by meter square, so that's why I can write length square, into rho means mass upon volume, so that's why mass divided by volume is there, so volume is nothing but length cube. So after this we can cancel out this length square into length cube, so only remain that force into time divided by mass upon length, right? Now I analyze for force. What is my force? Force is nothing but mass into acceleration. So mass into acceleration. Acceleration means what? Length upon time square, because meter per second square, meter per second square. So mass into acceleration means length upon time square. Okay. So now into time. So we can write like this, mass upon length. Now this mass get cancelled out easily, right? So here length becomes length square, and single time will be cancelled out. That's why time square is nothing but time. So length square upon time, that means meter square per second. So this is all about kinematic viscosity. So this is the relation between kinematic viscosity. Now move for the effect of viscosity. So this is the effect on temperature on viscosity. So in case of liquids, so when you increase the temperature, decreases the viscosity, right? And if you consider in terms of gases, if you increase the temperature, viscosity also increases. So this is the two phenomena for liquid and gases. So why it becomes like this? Because when you heating, or we can say we can implement the temperature, so what will happen? The cohesion bonding between the molecule is reduces, so that's why it can becomes less viscous, that's why viscosity will decreases. Cohesive bonding means it connect with each other. Attraction between two molecules is more, that is called as cohesion. So if you heated this, the cohesion bonding will be loose, so that loose bonding means the viscosity it can decreases. So the relation is like this, mu is equal to 1 by t, mu is equal to 1 by t. So mu is nothing but dynamic viscosity and t is the temperature, so this is inversely proportional. So this is the effect of temperature for liquid. Next for gases. So here when you increase, when you heating the that particular gases, so that increases the viscosity, because that molecular becomes more effective than that bonding. So that's why mu is the relation, mu is equal to T. Is it clear? So this is the effect of temperature on viscosity. Now next, the variations viscosity with temperature. So whenever you are to heating the gases, so it can predominate the molecular transfer, and it should be increases the temperature. So while that viscosity increases. So these are the relations for liquid and gases. So here relations is nothing but mu is equal to mu naught is nothing but 1 upon 1 plus alpha t plus beta t square. So this is relation for liquid, and for gases mu is equal to mu naught plus alpha t minus beta t square. So this is regarding the for gases, the relation between temperature. Now we move for the Newton's law of viscosity. So while expressing the viscosity is needed, so it's stated that the shear stress is directly proportional to shear strain, or can say velocity gradient. Okay, so the constant of proportionality is called as coefficient of viscosity, or we can say constant of proportionality. So that's why equation becomes mu is equal to tau upon du by dy. So that is called as Newton's law of viscosity. The next phenomenon is when the fluid which can obey the rule of Newton's law of viscosity, that is called as Newtonian fluid. So whenever the applying the that laws is there, so the Newtonian fluid is called as there. And if you does not obey the that Newton's law of viscosity, that is called as non-Newtonian fluid. Now we expressing this term, that is tau is nothing but shear stress, and that shear stress unit is Newton per meter square. And for du means change in velocity. Change in velocity means final velocity minus initial velocity. And dy means separated distance, or can say change in distance. So this is the difference. And du by dy means that velocity gradient of shear strain. So this is a description of units. So for tau we can take Newton per meter square, mu Newton second per meter square, mu, or you can say dynamic viscosity, Newton second per meter square. Du means change in velocity, so you can keep it as a meter per second. And for dy, that is you can take meter, so actually small m is required over here. And du by dy, so that is velocity gradient, so we can write it as a per second, or that s raised to minus 1. Why it is like this? Because du means change in velocity, it is measured in terms of meter per second. And for dy is meter, so meter get cancelled, only remain per second. So always remember that velocity gradient is in terms of per second, per second. So this is all about the Newton's law of viscosity. So now we discuss detail regarding the Newtonian fluid. So Newtonian fluid is nothing but it can obey the law of Newton's of viscosity. So for Newtonian fluid, the viscosity is entirely depend on the temperature and pressure of the fluid. For examples, water, air, and emulsions. So these are the figures, and here mentioning the different types of emulsions. This is the example of Newtonian fluid. And then next is a non-Newtonian fluid. So the fluid does not obey the laws of Newton's laws of viscosity. That is called as non-Newtonian fluid. So example is there, the pastes, or can say gels and polymer solutions there, starch solution is there, rubber is there. So all the example is the non-linear, or can say non-Newtonian fluid. So if you plot the graph between shear stress and shear strain, the curve is non-linear. That means it does not obey the rule of Newtonians. So now this is the example, gel, then starch in water, toothpaste. The example are non-Newtonians. Okay. Now we'll discuss regarding the types of fluid. So in the types of fluid, that ideal fluid is there. So ideal fluid, in that case, fluid is not that viscosity, that is called the ideal fluid. So here ideal fluid is there. So at that, on a x axis, on y axis it called as ideal solid. Ideal solid means it has more shear stress, right? It can resist very well, that is called as ideal solid. And for ideal fluid, it has less shear, means what? There is friction is zero, frictionless. The ideal fluid is called as frictionless. So this is actually imaginary fluid. Okay. The next is a Newtonian fluid. So already we discussed here Newtonian fluid. It obeys the laws of Newton's law of viscosity. The non-Newtonian fluid, it does not obey the law of Newton's law of viscosity. So that is called as non-Newtonian fluid. But for ideal, or can say plastic fluid, which when you define it as like this, the shear stress is having some ill value. So you can apply the shear stress, and after that, the relation between shear stress and shear strain is directly proportional. So that is called as ideal plastic fluid. So this is the content. So here clearly mentioned that ideal fluid. So ideal fluid, there is no viscosity, and it can have some that assumptions is there, that is called as imaginary fluid. Then real fluid, it can possesses the viscosity. So it can possess the viscosity. So it can something having viscosity. So different fluids is available with us. So the different fluids having different viscosity, right? So all the fluids are in practice is called as real fluids. And for Newtonian fluid, so it can obey the Newtonian law of viscosity, or you can say it can obey the shear stress is related to shear strain. So example is water, air, then oil. So this is example of Newtonian fluid. And for non-Newtonian fluid, the shear stress is not directly proportional to the shear strain, or you can say velocity gradient. So that is called as that non-Newtonian fluid. So example is toothpaste, then you can say gel, the sewage water. So these are the example of non-Newtonian fluid. Then ideal plastic fluid. So if you say that the shear stress is more than yield value, and after some time shear stress is directly proportional to shear strain, that is called as ideal plastic fluid. So CH sludge is there. So that is example of ideal plastic fluid. So now we will study the detailing of types of fluid. So here, we know that the Buckingham's fluid, that is called as ideal plastic fluid. So example is ketchup. So it requires more yield value, and after that the shear stress and shear strain is linear shape, that is nothing but directly proportional. So this is example of ketchup, or that fluid is called as Buckingham's or Buckingham's. Okay, the next is we can discuss here, that is diluent. So in diluent fluid, mostly that the solutions, the dynamic viscosity increases, the rate of shear strain will be increases. So example is the water plus corn starch. So this is shear thinking, okay, thickening, right? So that is called as that diluent. Then nextly, that is pseudoplastic. So in a pseudoplastic, you can say non-Newtonian fluid. So example is paint. So it is non-linear linearship between shear stress and shear strain. So shear strain is, always remember that, it on x-axis, and shear stress is on y-axis. So this is the phenomena in our types of fluids. So we'll discuss one by one. For ideal fluid, so ideal fluid, we can say that there is no viscosity, so it is totally frictionless. So there is no ideal fluid exist actually, and it is incompressible in nature. So it does not say that it is ideal because it is not existing one. So for flow of ideal fluid, it can flow like this. And for flow of viscous fluid, so at the center of the fluid or layer, it more viscous, or can say more having velocity, and as compared to bottom, or can say one of the sides, the shear stress is more, that's why velocity is zero, almost zero. And at the center, the shear stress is zero and velocity is maximum. So this is regarding the flow of viscous fluid, or you can say real fluids. So real fluid is the example that is compressible. So it is compressible actually in nature, and they're having some viscosity. So always remember that real fluid is having some viscosity. So example is kerosene, petrol, diesel, water, castor oil. So like that example is there. So for ideal fluid, we can put the values for velocities like this, because there is no friction. So that's why I can write stator manner. But in case of real flow, so it can decreases like this. The graph is changing like this. At the center, it's most velocity. At the bottom, or I can say at the wall side, there is a less velocity. So this is regarding the real fluid flow. Okay. Now next, that is the non-Newtonian fluid. We can explain brief over here. So in Buchanan fluids, that is finite shear is available with us. So that initially that is called as, example is drilling birds, or can say grease. So it requires more effort for initially, and then it can linearly relationship between shear stress and shear strain. So examples, toothpaste also. When you squeezing it, so squeezing it means what? It can require shear stress initially, and then we can obey the that law, that is shear stress to shear strain. Again, example is the sewage sludge, ketchup. It is Buckingham's fluids. The next fluid is pseudoplastic, or you can say non-Newtonian. Mostly that is called as categorized into non-Newtonian. So example is paint. So here viscosity goes on decreases with increasing shear rate. That stress is going increasing, so that that decreasing, so increasing the shear rate. So example is the paint or can say starch, detergent slurries. So this is the example of pseudoplastic. So it is non-linear shift. Non-linear shift means what? There is no relation between shear stress shear strain, only inversely. That is nothing but shear thinking or pseudoplastic. The next datum is there already discussed. That is example of beach sand or again say starch in water. So here the viscosity increases with increasing the shear rate. Okay, so this is the phenomena for the diatom fluids. Now next slide we discuss here pseudoplastic. So pseudoplastic is nothing but whose apparent viscosity decreases with increasing the shear rate. So example is ketchup, quicksand. Then we discuss here units. So in a last we will discuss the viscosity, that is dynamic viscosity. If you say only viscosity, so that mentioning like that dynamic viscosity, so that unit is mu. For mu is the unit, for SI unit is Newton second per meter square, already we discussed. And for British standard we express in a LB, okay, LBS per feet square, or in case of CGS we can write as dyne second per centimeter square for poise. So for conversion, for 1 poise to Newton second per meter square is 1 by 10, or you can say 1.1. So this is the importance for this unit for viscosity. And next viscosity is for kinematic viscosity. So meter square per second for SI, and for British standard we can write as a feet square per second. For CGS, that is centimeter square per second, or you can say stroke. So for conversion of stroke is the name of scientist. So one stroke to meter square per second is there. So that time we can multiply by 10 raised to minus 4. So easy here only conversion of centimeter square to meter square per second. So that's why 10 raised to minus 4 is there. So this is regarding the units. So basic difference between viscosity and kinematic viscosity is the relation for rho, that is nu is equal to mu by rho. Okay, so this is the regarding the units. So in next lecture we will discuss the regarding the problems. Thank you.